Regular martingales. This is a better way of constructing a martingale that actually turns up quite a lot. In this we have a random variable x, just one random variable this is, not a process or anything, just one random variable, and a filtration ft, indexed by times t, of sigma fields. And what we do is this. We define mt to be just the conditional expectation of x given ft. That's for all times t. So now we've got ourselves a process. Mt is a random function of t. Then that is a martingale. It's easy to see why it's a martingale. That just drops out from the way conditional expectations work. For any two times s and t, with s being the earlier one, the conditional expectation of mt given fs, so the conditional expectation of what it's going to be at the later time given what you know at the earlier time, that's the conditional expectation of conditional expectation and by the rules of conditional expectation the smaller sigma field wins. The smaller sigma field in this case is fs, that's the one for the earlier time, so this is just equal to the straight conditional expectation of x given fs, which is ms. And therefore this process mt is a martingale. It's conditional expectation of mt given an earlier sigma field fs is just what the m process was at that earlier time ms. So one line proof. So this is quite an easy way to make a martingale. If you've already got a filtration of sigma fields in mind, then all you have to do is think up one random variable, it can be any random variable at all, and just look at all its conditional expectations with respect to all of the sigma fields in your filtration, and you've got yourself a martingale. That might not look like any of the martingales we've seen previously, but in fact this is a very common form of martingales. Pretty much every martingale that we're going to run across is one of these. These are called regular martingales, the ones that have this form. So if there is some random variable x, so that everything in your martingale at every time t is actually the conditional expectation of x given the sigma field ft, that's called a regular martingale, and these are really common. Martingales that don't necessarily look like this at first glance often turn out to be of this form. Especially when we're dealing with a finite range of time. And this is something we'll be doing a lot. So far we've just assumed that time t starts at 0 and just increases from there and implicitly goes all the way to infinity. But quite often we're doing models where there is actually a final time, which we'll usually call capital T, and we're interested in the range of times between 0 and capital T. So if we have any old martingale just over a finite range of time like that, so just let that be any martingale defined for times between 0 and t. Well then, of course, xt is the conditional expectation of x capital T given ft, because that's the martingale property. Its value at any time is the conditional expectation of what it's going to be at a later time. If you take the later time to be the final time, capital T, then you get this. This is exactly the regular martingale form. It says that every value of the martingale at any time t is just the conditional expectation given ft of some fixed random variable. So now x sub capital T takes on the role of that fixed random variable. And there's a nice sort of an interpretation of this. You can think of this x sub capital T as a sort of final truth. That's what you would know when you know everything there is to know. When time gets to the latest time that it's going to get to, you're going to know as much as you're going to know. And what you know at that point, that's x sub capital T, and what you know at every earlier time then gives you a conditional expectation, which is the value of the martingale. So one of the ways of thinking about what a martingale really is that it's a process where the value at every time is just a conditional expectation of where it's going to end up, what its final value will be at the final time. So a martingale is revealed by that way of thinking to be quite a special thing. It's not really this broad class of stochastic processes. It is specifically a process that consists of a sequence of conditional expectations. Or, since we're dealing with continuous time, it's a function whose value at any time is a conditional expectation of what it's going to be in the end. Here's an example of a regular martingale. This is something I could have put in just as an example of a martingale, but I'm going to do it now as an example of a regular martingale because it's one of those two. This is Polya's urn. This is quite a famous stochastic process that is well worth knowing about in its own right. The story, or one possible version of the story that goes with it, is like this. We have a new model of phone just come out, and it comes in either red or blue. And everybody who buys one has to decide what colour they're going to buy, and the way they do that is they buy the same colour as one of their friends who already has the phone. Or to say more precisely what we mean by this, they buy the same colour as a randomly chosen person who already has one of these phones, a randomly chosen existing owner. So this is an example of what's called an imitation process. People are basically imitating each other. Of course, that does leave the question of how the first person decides what colour to buy. So we're going to make some exceptions for the first few people. The first few people are going to be early adopters who make up their own minds. After that, everybody will just imitate them. So if we let Rn be the number of red phones sold after the total sales are n phones, and Bn be the number of blue ones, so that is Rn plus Bn must be n. Then to start the process off, we'll suppose R3 is 1 and B3 is 2. So those first three early adopters, between them buy one red phone and two blue ones, and after that the imitation kicks in. Where does the martingale come in? The martingale is this. Rn over n, that is the fraction of all the phones sold out of the first n that are red. That's a martingale. If you like, that's the market share of red phones. Here, of course, Fn, the sigma field, is what you're supposed to know by time n. So that's the information you would have if you had seen the first n sales and what colour they were. In terms of random variables, we can write that as just sigma R1 to Rn. If you know those random variables R1 to Rn, you know everything up to time n. you know what colours all of those sales were. Let's just see why it's a martingale. It's a discrete time one indexed by n, so we have to look at mn plus 1 given fn. And if this is really a martingale, that should come out to be mn. So what is this? Mn plus 1. That's Rn plus 1 over n plus 1. So okay, we can just pull out the n plus 1, that's a constant. And what's Rn plus 1? Well, we'll do like we've done similar exercises before. That's Rn, how many red phones there were after n sales, plus possibly one more if that n plus first sale was a red phone. So that's the indicator of the n plus first phone being red. So let's see, the Rn, its conditional expectation is itself because it's already known by time n, so we can just put that there. And then we're left with the expectation of an indicator, which is a probability. So probability of the n plus first phone being red given fn. Now what's this probability? Well, now we come back to the process by which the n plus first buyer decides what colour to buy. They buy the same colour as a randomly chosen existing person. So let's see, how many existing owners are there? There are n at this point. And how many of them have red phones? That will be Rn. So Rn over n is the probability that they will randomly choose a person who already has a red phone, and they will therefore buy red themselves. So that is the probability, conditional on fn. Right, notice it is a conditional probability. It depends on the information you have available at time n. It depends on it because it involves Rn. Here we are, let's just fill in the rest like that. And now we just have to simplify this a bit. Take out the Rn. And we're left with 1 plus 1 over n, which is n plus 1 over n. So that's Rn over n, which is mn. So it's a martingale. The expectation, given what we know at time n, of what the market share is going to be after one more sale, mn plus 1, is whatever the market share is now. So that shows it's a martingale. What about being regular? Well, we don't have a final time here. N is going to infinity. So this is where we have to think, what is this sequence doing? This sequence, in fact, converges to a limit. Call it m. And the way to think about that is, mn is the market share of red, the fraction of n phones, fraction of red phones after n have been sold. And that converging to a limit means that ultimately this process converges on a kind of final market share, m, which is a random variable. Right? It's not a fixed number here. The final market share is a random thing, but the market share at every earlier time n is the conditional expectation of what it's eventually going to be. So that's what makes this a regular martingale, that the process itself has a limit, which also serves this role of being the final truth that every other member of the sequence is just a conditional expectation of. So that's the Polya urn. It's not always explained in terms of red and blue phones. More often, in a lot of probability books, it's explained in terms of an urn containing balls. And the rule is that every time you pick out a random ball, you look at what colour it is, and then you put it back in the urn along with another ball of the same colour. So that's the same story as with the phones. But it has of course, the same properties mathematically. It's completely equivalent, and in particular, it has this regular martingale associated with it.